Hey everybody, welcome back. We're just picking up where we left off in introducing you to vibratory harmonic motion. And now we're going to build upon those principles and jump into concepts of some basic wave propagation. And so for most of you, this is going to be your very first introduction to how we can compute and mathematically represent waves, harmonic waves that are traveling through different media. And this is very important when we want to model earthquake waves and how they travel through either soil or a structure or any material for that matter. So let's just begin with the very, very basics. In introducing this topic, let's imagine that we have just a metal rod and it's infinitely long. So you can see here I have these cut ends here, and that just implies that rod goes on forever in both directions. Also, the rod is completely surrounded by these rollers, and it's confined by these rollers. So what that means is that the rod is free to move within those rollers. In other words, like a slinky, it can kind of move back and forth side to side, or it can twist within those rollers, but there's no bending or there's no compression or bulging of the rod whatsoever because it's constrained. And so because it's constrained, this rod is going to have a couple of different properties. The metal rod has a rho, which is a mass density. It also has a Poisson ratio. In other words, how much would it want to bulge if we were to compress it, or how much would it want to contract if we were to stretch it out. And then finally, it has a modulus value. Now, when we're dealing with materials that are constrained and aren't allowed to bulge or bend in any way, then they have a special elastic modulus that we call the constrained modulus. And it's directly related to Young's modulus, or the elastic modulus, and it's related through this relationship right here, which is a function of the Poisson ratio. So it's not exactly the same thing, but it's related. Okay, and so if we look at the rod, if we just look at some partial section of the rod, we can call that dx. So this is just one little section or segment of the rod, and the rod has a diameter equal to d. So because this rod is constrained, waves can travel down this rod in one of two ways. So you could imagine if I'm on the end of this infinite rod, which I know by definition is impossible, but just bear with me here. Use your imagination. So I'm on the end of this rod that's going off to infinity in the other direction. If I take the end of that rod and I bang it with a hammer right on the end, it's going to send a compression wave all the way down through my rod. So that compression wave is causing stresses and displacements that are longitudinal with the orientation of the rod. So it can have longitudinal waves. But also, I could grab the end of this rod and just twist it. Give a big twist to it. And that twisting will propagate all the way down through the rod as well. And that type of wave propagation is what we call torsion. So that would be a torsional wave that I would be instituting in my rod. Excuse me. So now we get to the fun math part of the equation. And rather than walk through and derive 3 days worth of equations, what I've really chosen to do in this presentation is boil it down to the nitty-gritty. And anytime we derive any sort of relationship for motion, we need a couple of things. The first thing we need is an equilibrium relationship. So this is the fundamental key. This is something that's going to relate stress. It's going to relate stress from the wave to displacement from the wave. So that's my equilibrium displacement. The next thing I need is I need compatibility relationships between stress strain and strain displacement. So again, this is going back to that principle of I can't solve a system of equations for a larger number of unknown variables than equations that I have. And so because I don't know displacement and I don't know stress, I need a series of two sets of equations. So equilibrium relationship and stress strain, strain displacement compatibility. So looking at longitudinal vibration, here is my equilibrium relationship. We could spend a class period and derive this. This wave equation, by the way, was solved many decades ago, so I don't see any purpose in re-deriving it. If you're interested, you can go into the Kramer textbook and walk through the derivation of the wave equation. It's kind of interesting. It's a fun exercise, but I'm not going to do it here in the lecture. So here's the equilibrium relationship for a longitudinal wave, and here are our stress strain and strain displacement compatibilities, where again m is our constrained modulus, rho is our mass density, x is the location along our rod, u is the displacement of the rod in the longitudinal direction, and t is time. So what we end up with is this term Vp, and again remember that's the p wave velocity. That's the propagation velocity of a p wave in our rod. Okay. So it comes out equal to that, and the p wave, the propagation velocity, mathematically we can derive it as a simple relationship between mass density and constrained modulus. So it's just the square root of the modulus divided by the mass density, and this little relationship right here, my friends, this is a jewel of a relationship. This relationship is used by geophysicists all the time to relate dynamic properties of soil to things that are of interest to us, like stresses and strains and displacements. And so this relationship here is really, really important. And the reason for that is because we can physically measure the p wave velocity in soil. And if we can measure it, then we can calculate what its modulus and what its density are. So this equation right here is what we call the one-dimensional longitudinal wave equation. And so you can see it has some double derivatives in it, and it relates displacement with time to displacement with location on the bar. So our two variables in the equation are time and location on the bar. And as we said before, V sub p is the propagation velocity. Now, this propagation velocity, that's the velocity that a compression stress wave will pass through the rod. But this is important. It's not the same velocity that a single point on the rod would move as the wave passes through it. So in other words, a point on the rod, the physical velocity that point moves back and forth as the wave passes through it, that's a different kind of velocity. That's what we call the particle velocity, or u dot. Okay, and so that's simply equal to the change in displacement versus change in time, and we could derive from our wave equation that it's a function of the longitudinal stress, the normal stress acting on our rod, or how much our rod is being compressed. And so some points to take from this is that this particle velocity is a function of the axial stress. So the tighter I squeeze that rod, the more compressed it is, the faster that particle velocity will be as the wave travels through it. However, the propagation velocity, this v sub p, right, that propagation velocity is simply a function of modulus and also of the mass density. And it's a function of nothing else. And so it doesn't matter what the stress in the rod is, that propagation velocity is going to travel through the rod at the exact same speed, the exact same velocity. And the only way to change it is if I change either the mass of the rod or I change the constrained modulus. So understanding the difference between particle velocity and propagation velocity, that's conceptually important to understanding how to use the wave equation. Okay, so that was the first scenario, hitting the end of my rod with a hammer. But now let's go to where I'm grabbing the rod with my hands and I'm applying a twist to it. So I'm grabbing the end of it and I'm just twisting it. And now that twisting motion sends this twist all the way down the rod. And it's not a permanent twist. It's just one big twist and then I relax it and let it go. Now that twist is going to travel all the way down my infinite rod. And it's going to cause a twist of d theta, an angular torsion or a rotation in my rod. And it's going to cause a torque that we call T sub x. And that's equal to the torque that I applied on the end of my rod. And so the torque at any location dx along our rod is equal to my initial torque plus the change in torque with the change of x times dx. So, like before, here's my equilibrium relationship. And that's going to now relate torque with angular distortion, theta. This j that's in here, that's the polar moment of inertia. Maybe you guys will remember that from statics. And then I need my stress strain and my strain displacement compatibility, so I plug those in to my equilibrium relationship and I end up with the wave equation for a torsion wave. Now you're going to notice if you pause this and go back and look at the wave equation for a longitudinal wave, this relationship is the exact same with the exception. Instead of u for displacement, we have angular distortion theta. Instead of constrained modulus m, we have shear modulus g. And instead of propagation velocity or p wave velocity, we have shear wave velocity. This is the propagation velocity of the shear wave in my material. And so you can see the formulation is the exact same. All we're doing is swapping out terms that relate to torsion instead of terms that relate to compression. And as before, we can derive a term that uses dynamic soil properties to come up with our S wave velocity of the material. And it's simply the square root of the shear modulus divided by the mass density of the material. And once again, this propagation velocity is constant for the material. It does not matter how much it is stressed. It's constant. The only thing that changes it is if we change the modulus or if we change the mass density. And one of the cool things is, again, geophysicists, we can measure shear wave velocity in materials. And from that measured shear wave velocity, we can calculate what the shear modulus is and what the mass density is. So let's just talk now about the one-dimensional wave equation in a generic sense. Now, whether we're dealing with a longitudinal wave in our rod or we're dealing with a torsional wave in our rod and harmonic vibrations, this 1D wave equation is going to be of the form that looks something like this. And the only thing that changes is whether we use U or theta, whether we use P wave or S wave, and that's pretty much it. Everything else is essentially the same. So if I take now this equation and I do some differential equation work on it, the solution to this partial differential equation is going to take the form of an equation that looks like this, where we have two functions, f and g, that are both functions of the propagation velocity of the material, also of time, t, and also of location along our rod, x. And those f and g functions, those are arbitrary functions that satisfy our particular differential equation. So now, rather than just looking at one pulse loading that we put into our rod, like what I just described, let's assume now that we have a steady steady harmonic loading going in. So now I'm sitting on the end of the rod just banging it with a hammer at a regular frequency, or I'm holding the rod and I'm torquing it with a regular amplitude and a regular frequency. And so the stress coming from those waves is a function of time. And that function of time is simply equal to my initial stress. So every time I hit it or every time I torque it, that's the stress that I'm putting into the rod. That's my initial stress. And I'm applying that stress at a circular frequency equal to omega bar. So that just describes how many radians are passing of time before I apply the next load of stress into the bar. So now we have simple harmonic periodic motion going into the wave now, or going into the rod. Now, from what we learned in the last lecture on vibratory motion, we could take our solutions from alternate trigonometric notation, and we can apply it to that wave equation, and the solution to the wave equation therefore becomes an equation that looks like this, where a and b are the amplitudes of our two functions, of the waves of those two cosine functions. They're both applied at the same circular frequency of omega bar, and we are now have some sort of phase transformation in our waves that's a function of what we call k. And k is a number that we can derive. It's called the wave number. And so it's a common dynamics term, and it's just equal to the circular frequency of loading divided by the propagation velocity of our material. So whether we're dealing with torsion waves and using V sub s in there, or we're dealing with longitudinal waves and we're using the p wave velocity, we can compute the wave number for those waves that we're putting into our material. Alternatively, if we don't want to use alternative trigonometric notation, we can use the Eulers method and write it in terms of a complex notation, where now we have real numbers and imaginary numbers. And that function simplifies dramatically to an equation that looks like this, where now the amplitude of our two waves are going to be equal to c and d respectively, and they're being loaded at frequencies that can be described with these wave numbers and circular frequencies. So here in this type of notation, the first and the second terms here, these are describing harmonic, just simple harmonic periodic waves that are propagating in the positive, right there, and in the negative directions along our rod, respectively. So think of it almost as, let me get here and clean off my whiteboard. If I have a rod, think of this notation as I have one wave that's coming this way, and I have another wave that's coming this way. And at any given time, we're just summing those two waves to get our cumulative wave of whatever our displacement along a given point and the time along our bar is. And so when we add these two waves, each moving in the positive and negative x directions respectively, we end up with our total displacement And then the wave number is related to a term that you're probably familiar with, wavelength. And so this is just the physical distance. If I have waves traveling along this rod, that wavelength is just the physical distance from peak to peak or from trough to trough. So that wavelength of the waves traveling along my rod, we can relate it to different terms. We can relate it to the frequency of the waves, and that's just the propagation velocity divided by the frequency. We can relate it to the period of the waves, and that's the propagation velocity times the period of the loading. We can relate it to the propagation velocity and the circular frequency of loading. So this is just, you can see we're dealing with 2 pi, so we're dealing in units of radians. Or we can relate it to the wave number of the material and the loading. And so there's all sorts of relationships that can be derived between these different wave descriptors. And this relationship right here will come in handy for us a little bit later on when we want to solve for some different dynamic properties of materials. Okay, so what does this mean? I have a function then that we have, whoops, I don't want to give my thunder away. So we have a function u that is a function of x and t equals, and we can write it in complex notation or we can write it in alternate trigonometric notation. But the point is that this function, this function of motion, this wave equation, is it's a function of both time and position along our bar. And what does that mean? Well, let's say that I'm interested in, for a constant value of x, I want to vary time. So what that means is, imagine I have a bar and I have a single point on that bar, and I just want to track how that point is going to move back and forth along that bar with time. So if I'm tracking a single point along the bar, that could be plotted using the wave equation as a function like this. So what I see is my point moves up in one direction, and then it moves back to the other direction, and then up in another direction, and so it's just moving back and forth as a function of time. So the wave equation allows me to do that. So in other words, this is representing a given or a fixed location of x on the bar. The displacement history of that fixed point on the bar is equal to this function here. Alternatively, let's say that I want to fix a value of time and I want to vary location along my bar. So now this is like a snapshot in time of what my bar looks like. So now I'm just plotting, if this is my bar and I have, I have a lot of compression, and then, man, I have no idea how to draw this. So let's say that I have compression and then tension and then compression and then tension, compression and tension along the bar at any given time t. So this plot right here is saying, given a snapshot in time, at time equals t, the shape of my bar is equal to this plot right here. So x just gives location along my bar, and this just gives the displacement of my bar for any given point of x. So the wave equation is powerful because it can give us the displacement time history for any point along the bar, and it can also give us the shape of the bar for any snapshot in time. So it is a very powerful function. Okay, so let's get into some dynamic properties of materials stuff. This is a very common thing that we need to do if we want to be able to solve the wave equation for different types of materials. We have to be able to characterize the different wave properties of that material. So this is just an example problem that's coming out of the Kramer textbook. And let's just assume we're dealing with the property or the material steel. Now for steel, let's compute the propagation velocity of that steel. Let's compute the torsional wave propagation velocity, the S wave velocity. Let's compute the wavelength if we're putting in harmonic loading at a frequency of 10 hertz. So 10 cycles per second of loading. And then let's look at the wavelength from a harmonic torsional wave if we apply a torsional wave at the same frequency of 10 torsions or 10 cycles per second. So here's what we know about our steel. This is given to us for a material of steel. We know that the specific gravity of the steel is equal to 7.85. That means that the mass of steel for one given ounce or 1 gram is 7.85 times the mass of water. The constrained modulus is equal to 40.4 times 10 to the 6th psi. And the shear modulus is equal to 11.5 times 10 to the 6th pounds per square inch. So those are my moduli. So let's go ahead and solve these problems. So the first thing we want to solve for is the P wave velocity, the propagation velocity. And we're going to use our simple relationship that relates constrained modulus with mass density and the propagation velocity. Now, this term here was not given to me, but I can derive it if I know the specific gravity. So it's simply equal to the specific gravity of the material I'm dealing with times the mass density of water. So mass density of water, that's a pretty known value. I don't know it off the top of my head. That's something that we're not regularly taught in American engineering. But we are taught the unit weight of water, which we know is 62.4 pounds per cubic foot. We memorized that like on our second day of engineering school in the United States, it seems like. And so the mass density is simply equal to the weight density divided by gravity. So all I'm doing here now is some manipulation of some material properties that I know. So now with this equation, there's everything in there I know. I know gravity, it's equal to 32.2 feet per second squared. I know the specific gravity of material, it was given, it's equal to 7.85. I know the unit weight of water, it's equal to 62.4 pounds per cubic foot. And I know the constrained modulus of my soil. It's 40.4 times 10 to the 6 pounds per square inches. But I need unit compatibility, so I need to convert from square inches to feet squared. So I do all these unit conversions, and I solve the problem, and I come out with a P wave velocity of 19,556 feet per second. So that's pretty amazing if you think about it. That's like more than 3 miles per second. So if you pound that rod and with one hammer blow and you just wait, within 1 second that wave has traveled almost 3 miles down the rod. Pretty incredible. Okay. Now let's do part B. Same thing, same calculation, but this time we're getting the shear wave velocity, the torsional propagation velocity. And so the only difference is we're going to use our shear modulus instead of our constrained modulus. Everything else is going to be the same. So I just plug in that 11.5 times 10 to the 6 pounds per square inch, and I pull the crank and I get 10,434 feet per second. So that's about 2 miles per second. So if I apply torsion on the end of my steel rod, within 1 second that torsion wave will travel about 2 miles down the length of the rod. Okay, now if we were applying harmonic loading at a frequency of 10 hertz, what is the wavelength. So in other words, every time we apply some new stress or a new torsion to our rod, it's going to immediately begin traveling down the rod. And I want to know how far it travels before I apply the next stress. And that will be my wavelength. So using those derivations, those relationships of different wave properties that relate to wavelength, I'm just going to find one that I know that relates to the terms that I know. I know the propagation velocity because I just solved for it. And I know the frequency of the loading because, well, it's given to me. And so I can take these terms then that I know and just perform the calculation, and I end up with 1,956 feet between waves. And that's if they're being applied 10 cycles per second. Now, looking at the distance between the torsional waves, it's the same calculation, but this time I'm using the torsional wave propagation, or the S-wave propagation velocity, and do that calculation, and it's 1,043 feet between troughs or peaks on my waves that I'm applying to my steel. So this is how we can do some calculations to get various dynamic and wave properties from different materials. So now that you're prepared in some of the basics of waves traveling through a single type of material, a homogeneous material, what happens when waves travel through two different materials? So in other words, our rod is half of it is comprised of material 1 that has these properties of mass density, modulus, and propagation velocity for that material. But then somewhere along the rod there's a transition, and it changes to material number 2. And it has totally different dynamic properties. And so if we have this wave that's traveling from left to right, what is going to happen when that wave reaches this interface, and what type of waves are we going to expect? So let's say that I have this wave traveling from left to right, and it's traveling through material 1. It's what we call the incident wave. So when you hear incident wave, think about this as like the initial wave, the starting wave. So here's my incident wave. It's traveling from left to right, and it comes in and it hits that boundary. When it encounters a boundary of another material, part of the wave is reflected, so part of the wave is going to bounce back and go back the other direction in material number 1, and part of the wave is transmitted. So part of the wave moves into material number 2, and it may have a different amplitude, it may have a different frequency, but it enters the second material and it just continues as it did before. So this is wave dynamics. Whenever we have an incidence, when we have two materials that meet each other, we call that an incident. And whenever we have incidence, we will always have wave transmission, and we'll have wave reflection. Okay, so let's use what we learned about the wave equations to see if we can come up with some equations to predict what the transmitted stresses and displacements would be, as well as the reflected stresses and displacements. So we're assuming we know the incident wave stresses and displacements because we created them. But we want to now predict what the reflected and the transmitted displacements and stresses are going to be. So we can describe these waves either in terms of stress or displacement. And whenever you see a subscript I, that means our incident wave. If you see R, that means our reflected wave. And if you see T, that's our transmitted wave into the second material. So we can describe, using complex notation, the formulation of our incident wave is equal to this. And you'll see, by the way, that it has a little subscript 1 for our wave number, and that means that we're traveling through material number 1 on our rod. And with the reflected wave, you'll see that the wave number still has a 1 in the subscript, which means that now we're still in the first material, but notice that the sign changed. Here's the sign for the incident wave. It's negative, meaning that it's going from left to right. But now it's positive, which means that it's going the other direction, from right to left along that material. So that represents a reflected wave. Notice now for the transmitted wave stresses, however, we see that we're using the wave number from the second material. So we're now in the new material, and from the sign, we see that the wave is traveling in the same direction as the incident wave was, which was from left to right. We see the same stuff over here in displacements. The only difference is that we're using displacement instead of stress, and the amplitude of our waves, we're using a different value. We're using A for amplitude for our initial displacements instead of sigmas. All right. We can use the same principles we use to derive the wave equations, meaning that we need equilibrium relationships, and we need stress strain and strain displacement compatibility. And if we do that and we walk through all the derivations, we would end up with relationships that look like this for our 3 types of waves: our incident, our transmitted, and our reflected waves, respectively. And some of these things you're going to notice. For instance, notice here's stress, and stress is a function of modulus and strain. And that relates to something that you've already learned. Remember PL over AE? Whoops, not AU, AE. Yeah, do you remember that relationship of stress? Stress equals PL over AE, and you guys learned that material. It's the same concept. We're just dealing with a modulus, and we're dealing with a strain in a material, and we're relating that to stress. And then we're using what we learned from our wave equation derivations to instead plug them into a wave equation compatible format. So if we do the math and we simplify these and these differential equations down, they boil down to equations that look like this. Much more simple, okay? And a few things you'll notice. Again, the transmitted wave, you'll see subscripts for 2, meaning we're in the second material of our rod. And for the reflected and for the transmitted waves, you see subscripts of 1, which means that we're still in the first material of the rod. Now, here's the trick that makes all of this work. If I have this rod of 2 different materials and it has a boundary, right at that boundary between the 2 materials, there has to be compatibility between stresses and displacements between those 2 materials. Otherwise, there would be separation between the bars, and we don't want separation between the bars. So we have to satisfy these boundary conditions right at the boundary between the 2 materials. And here are the 2 boundary conditions that we're going to satisfy. First of all, the summation of the incident and reflective waves for stresses have to equal the transmitted stress wave. And similarly for the displacement waves, the summation of the incident and the reflected displacement waves have to equal the amplitude of the transmitted wave right at the boundary between our 2 materials. So we can take this boundary condition, and then we can take our derivation of the wave number for our 2 different materials, and we can simplify these relationships down mathematically to come up with some relationships that we can use to get the ratios of how our wave amplitudes change depending on which wave we're dealing with. So let's focus on displacement amplitudes first, okay? So what this means is if I want to know the displacement amplitude of my reflected wave, so this is the wave that bounces back from the boundary, it's going to be equal to this ratio here of these different dynamic properties. And you can see it's properties of the first material, the mass density and the propagation velocity of that material, and it's a function also of the mass density and the propagation velocity of the second material. That ratio creates basically a factor that we multiply by the initial incident wave, which we know. So if we simplify this down and we say that this ratio of the mass density from the second material times the propagation velocity from the second material divided by the mass density times the propagation velocity of the first material equals a term that we call the impedance ratio. So, impedance, by the way, has a very special term. Impedance implies that it's a boundary between two different materials, and there's going to be some impedance is the very act of waves transmitting and reflecting. So whenever waves hit a boundary between two materials, they always transmit and reflect. That act of doing that is called impedance. So this ratio of dynamic properties between the two materials at the boundary is called the impedance ratio, and we represent it with this alpha sub z. So I can take this relationship here and simplify it into this equation, where now if I know the incident wave amplitude and I know the dynamic properties of my two materials in my rod, I can predict what the amplitude of the reflected wave is going to be. Similarly, I can predict what the amplitude of the transmitted wave, displacement wave, is going to be in my rod. And it's simply equal to this ratio right here. Now, again, these are displacement amplitudes. Let's look at stress amplitudes. Same concept, but now we're dealing with stress waves. So if I want the stress wave of the stress amplitude of the reflected wave, it's equal to this factor times my incident stress. And if I want the transmitted stress amplitude, it's equal to this factor right here, where again, remember that alpha sub z is my impedance ratio. And it's just equal to rho 2 times the propagation velocity 2 divided by rho 1 times the propagation velocity of 1. Okay, so let's look at a couple special cases. What happens if my rod has a free end? So my rod ends, and it ends right just to atmosphere. Okay. Well, imagine, or use your mind to imagine that this rod continues off to infinity, but now this mass right here is equal to 0 because the air is basically has no mass relative to the steel. Okay, so if I plug this in here, and I solve for my impedance ratio for this material, where my mass of my fictional bar is equal to 0, my impedance ratio goes to 0. Now let's look at another scenario where, let's say, my rod runs into a fixed end. I would joke with my students and say, imagine the rod runs into Dr. Frankie's bicep, because my bicep is so solid and rock hard. But I'm turning 43 this year, and that's really not the case anymore. So let's imagine that rod runs into something that's really, really rigid and hard, infinitely rigid, in fact. So again, we imagine now that this rod is just continuing, but in this case now the mass density of this second material is equal to infinity. Well, because it's rigid, it's infinitely hard. If that's the case, then my impedance ratio is also going to be equal to infinity. So I can take these special cases and go back, I'm moving backwards through the slides, and I can use these relationships to figure out what those special cases would do for my waves, my amplitudes of my reflected and my transmitted waves. So in the first case, here's what we see. For this first special case, the transmitted wave right at the end of my bar is doubled, meaning right at the end the displacement lurches and does a big double, okay? A double displacement. And that's a big deal because it could really damage my material right there at the end. The reflected wave is equal to the incident wave, so it's just a straight reflection. It doesn't change the direction. I'm sorry, it doesn't change the orientation of the wave. It's just the direction has changed. The stress at the end of my wave, by definition, is equal to 0. In other words, I can't transmit stress into the air. So we're saying that the transmitted stress at the end of my rod is equal to 0, and the reflected stress is equal to negative of the incident wave. This has really practical applications, particularly in an area that maybe some of you aren't familiar with, and maybe some of you are. Let's look at the application of pile driving. So here's my ground surface, and I want to build a new building. And so I'm driving a new pile into the ground. Okay. Now let's say that somewhere down here I have a really soft soil layer. So soft that this pile that I'm driving down through this soil meets almost no resistance here at the end of it. Okay. So here I am, I'm dropping this hammer and it's banging up here on the top of my pile. And what that's doing is that's putting a compression wave all the way down to the end of my pile. And it's hitting the end of my pile, and if the impedance at the end of my pile is very close to 0 because the soil is so soft, what ends up happening is this point here at the end of my pile does a double displacement. And so it literally rips off of the end of my pile. And then the wave that travels back is in the opposite loading of the incident wave. So if my pile driving sent a compression wave down my pile, and I have 0 impedance down here at the bottom of my pile, then I'm going to get a tension wave traveling back up through my pile. And the tension wave is going to have the exact same magnitude as the compression wave did when I originally drove it. Now, for those of you who've done anything with, say, reinforced concrete, what happens when I apply a big tension to reinforced concrete? That's right. It spalls, it cracks, it breaks, it pulls apart. And this is what happens if I'm driving concrete or wood or reinforced concrete piles through really, really soft soil. Is I can develop tension rebounds in my pile that will literally rip my pile to pieces and render it useless. And so this science, my friends, of driving piles is a big deal. You can't just go out there with any old hammer and pound piles into the ground. You have to size the hammer to the pile and to the soil conditions you're expecting so that you can maintain the integrity of your pile. So anyway, that's just one example of these principles of impedance that we're talking about here. Now, what about this other special scenario where now we're running right into a fixed end? So this would be like the case of a pile being driven right into solid bedrock. If this is the case, then the transmitted wave, or the transmitted displacement right on the end of the pile is equal to 0, which makes sense because now you're basically trying to drive this pile into an infinitely strong material. So I wouldn't expect any displacement to happen. The reflected wave is equal to the incident wave, just an opposite displacement. Now check this out. The transmitted stress going into the rock or going into the fixed end is double the incident stress that came into it. So in this case where we had a free end, we doubled the displacement amplitude. In this case where we have a fixed end, we're doubling the stress amplitude at the end of our bar. And the reflected stress is equal to the incident stress. So if I go back now to my little pile driving example that I gave you, and let's say this now was solid rock that I was trying to drive my pile into. I'm not so worried about ripping my pile apart now because the reflected waves that are coming back are going to have the same direction as the incident waves. So they're going to be compression waves coming down and compression waves going back up. However, right here at the transmittal, at the impedance boundary, my stress doubles. Which means if I have a lot of stress coming down this pile into this solid rock, I could be causing all sorts of fracturing of the rock down here, fracturing or brooming of the end of my pile. And so I could be really damaging the very end and tips of my piles and the rock that I'm trying to seat my pile into. All because of this concept of impedance. Driving a rod into a fixed end boundary. So using those ratios that I gave to you, you guys could create your own table like this, but I'm just giving this to you for your own convenience. What this gives you is for different values of impedance ratios, for different materials, different impedances. This gives you the resulting incident, reflected, and transmitted displacement amplitudes and stress amplitudes. So it might just save you some calculation. And again, remember, if I have zero impedance, that's the same as a free end case. And if I have infinite impedance, this is a fixed end case. All right, well, we're going to end up using these impedance values as we predict how waves travel through different media of soil. So instead of dealing with steel rods, we're going to be looking at soil. So every time a wave travels and hits an impedance boundary of different soil layers, like from clay to sand, from one type of sand to a different type of sand, from sand to gravel, whatever that change in material is, we're going to get some transmission and we're going to get some reflection. And we'll be dealing with that in a future lesson. But for the time being, I hope you enjoyed this introduction to how we can calculate and quantify waves in terms of displacement and stresses as they travel through different media. So I appreciate your attention today, and I'll look forward to seeing you in the next lesson. We're going to talk about part 2 of waves traveling through different media. We're going to talk about what happens if the waves are coming at an angle. So we'll deal with Snell's law, and we're going to be predicting, in essence, all of these reflections and transmissions. So that's going to be a really, it'll be a fun activity. You'll see what I mean. But anyway, appreciate your attention. Have a wonderful day.